she did her bachelor in Carnegie Mellon University in electrical and computer engineering with a double major in computer science. And she has a lot of awards, including DAC Under 40 Innovators Award, Google Research Scholar Award, NSF SRC Energy Efficient Computing from Devices to Architectures Program Award, Intel Labs Gordy Academy Award, and several other Intel recognition awards, and also an Outstanding Dissertation Award from European Design and Automation Association. And she, of course, has several Best Paper Awards. And today she will talk about how does one bit flip corrupt an entire deep neural network and what to do about it. And this is a topic that is very relevant to our current research as well, and we find it fascinating. So we're really excited to hear what you have to say.
Great, thank you so much for the introduction. One more thing I would say that's not on my kind of bio is that Honor and I actually collaborated while I was a grad student, and we're still collaborating now, actually. So hopefully I'll have a lot more interactions with the group in the future. So let me get started with today's presentation. Before I start, I would just like to acknowledge the students in my group. They are doing all the hard work, as well as our collaborators and sponsors. The title of my presentation is How Does One Bit Flip Corrupt an Entire Deep Neural Network and What to Do About It? So what do I mean by bit flips? What I really mean is basically bit flips that occur in the hardware circuit because of some hardware failures. Hardware failures can lead to malfunctions in electronic systems, and then severe consequences such as productivity loss, financial loss, or even loss of human life. As our world is more and more dependent on electronic systems, being able to be resilient to these hardware failures and continue correct operation in the presence of these failures is much more important than ever before. And there are many different types of hardware failures, which can be broadly classified into two different categories. The first category is the so-called temporary or transient hardware failures. Their effects are temporary, as the name suggests. So any bit flips that occur as a result of these failures will only occur for one or at most a few cycles, and then they would go away. So some examples include dynamic variations, circuit marginalities, and soft errors. We also have a second category called the permanent hardware failures. So here the effects are really persistent, and the bit flips may persist for many cycles through the system's execution. And I've also included some examples here: early life failures, circuit aging, and manufacturing defects. And hardware failures pose very significant challenges. Very recently, just within the last 2 years, we have heard all kinds of horror stories from hyperscalers, including Google and also Facebook. They call it the silent data corruption challenge in their data center systems, which are basically hardware-induced errors that somehow escaped all error reporting mechanisms, and then they propagate and manifest as application-level problems. The problem has become so severe such that the hyperscalers and also chip vendors such as Intel and AMD, they basically came together to form a working group to address this challenge. Now, hardware failures and silent data corruption, they are not actually new problems. There are actually many techniques in the field of fault-tolerant computing, testing, and validation, and so on. However, even though we have very rich literature, it is not helping with this challenge that we're facing today, because there are several important and major factors that are different now compared to before. So before, we're talking about failure rates of 1 in millions of devices, but today, the failure rate that we're observing is 1 in thousands of devices. So this is orders of magnitude difference. Also, in the past, we mainly focus on soft errors and also very high-end and safety-critical systems. So the solutions tend to be costly. But today, all types of hardware failures have been observed, and it is a wide concern affecting all kinds of systems, even the very cost-sensitive data center systems. So existing solutions that are costly are no longer adequate. A major focus of my research is to overcome this challenge And we have done a lot of work targeting various types of hardware failures and also different systems. This is not actually the topic of today's presentation, but I would just like to take the opportunity for a few minutes to highlight one of our previous work, which enables a general purpose system to test itself in the field concurrently with normal operation to detect or even predict occurrences of major sources of hardware failures while incurring very, very low cost. We have received many awards and recognitions for this work, but what I feel the most proud of is that the derivatives of our work have been used by various companies such as Intel, NVIDIA, Synopsys, Renesas, TI, NXP, Meta Graphics, and so on. And for both automotive and data center systems, we have also some ongoing efforts to expand the impact of this work to cover even more systems and applications. So if you're interested, please feel free to reach out, and I'm always happy to discuss more. Now, back to today's presentation. Our focus is on deep learning, and I don't think anyone here would argue the importance of deep learning, as it has revolutionized many aspects of technology and has completely transformed our lives. But when I mention hardware failures and deep learning together, the reaction that I often get is this: isn't deep learning already inherently tolerant to all kinds of errors and noises and so on? And the answer is, although these applications are stochastic in nature and can tolerate some errors and some noises, they cannot tolerate all errors. And hardware failures can lead to many undesirable consequences in deep learning applications. For both inference and training, we may run into numerical errors, such as infinities and NaN values in a floating point representation. We may also encounter hardware configuration errors, which may lead to lower utilization of the hardware resources and also lower performance of the applications. We can also run into things like hangs and crashes. For inference workloads, hardware failures can result in reduced inference accuracy. And then for the training workloads, the whole process may just fail to converge. And also both the training and test accuracy may be affected significantly. Deep learning applications can be run on different hardware systems. And here our work focuses on deep learning accelerators, which are hardware designs that are tailor-made to optimize deep learning applications. So these accelerators are widely used for both inference and training purposes in different application domains. So our goal is to enable resilient deep learning accelerator systems, so these systems can continue to operate correctly, even in the presence of hardware failures. And to achieve this goal, we must answer two key questions. First, we must thoroughly understand the impact of hardware failures on these systems and workloads. And secondly, we need to mitigate these hardware failures efficiently. We surveyed a large space in existing literature. There are existing resilience techniques for inference workloads, but they are very, very limited in scope. For example, they target memories only and completely ignore the processing logic. Training is even worse. We only found one paper, but again, the scope is limited as that work only analyzes memory errors in training. There's, of course, a lot of work for general purpose systems. For resilience analysis, the most widely used approach is fault injection. But existing techniques all suffer from limitations, which I will discuss in more details in just a little bit. And in terms of mitigation techniques, although there's very rich literature in fault-tolerant computing, as we talked about earlier, the solutions tend to be very costly. So as you can see, there are really some major gaps here. And in my group, we have made significant contributions to both understanding the impact of failures as well as mitigating them. We cover both training and inference workloads, transient and permanent hardware failures, and hardware failures that occur in both logic and memory. So we covered the entire problem space to really advance knowledge and really closing these knowledge gaps in the literature. And moreover, we're working with Google and Hitachi to aim for technology transfer of our work. In the rest of the presentation, I am going to provide a deep dive into how transient hardware failures in logic affect deep learning training workloads. A big part of this work is a collaboration between the University of Chicago and Google, and we publish this work in ISCA and Micro. So you can always refer to our papers for more details. As I promised in the title of this talk, I will show you how a single power bit flip can actually corrupt the entire training process of a neural network and what we can do about it.
Professor Lee, sorry to interrupt, but before going to those papers, we have a question on YouTube actually.
Okay, go ahead.
The question says, do you think better testing before chips are shipped? Do you think testing the chips before they are shipped can to a certain degree solve these errors? Can we reduce error rates to 1 in a million, for example, if we perform better testing methodologies before shipping the chips?
Yeah, so of course, right, all systems are tested before they are shipped. Like even today, there's very thorough testing that's going on. But the thing is, that's still not sufficient. And that's due to a lot of reasons, a lot of problems, basically, they don't show up, right? And the truth is, there's lots of failure mechanisms that we don't yet completely understand. So we don't have the accurate driving metric to even basically predict all kinds of problems that can occur in the field, and then use the adequate like test metrics and test patterns to screen out all problems. And also, if we want to do that, the cost will be extremely high during the manufacturing phase, and nobody can afford to do that basically. And some problems, of course, only occur in the field. So even if you have tested a system completely, right, we cannot do that. But even let's say we can do that right now, it's still not safe because as the systems are running in the field, problems can keep occurring. So we don't believe, right, that just by testing itself can completely eliminate the hardware testing problem. As you can see from this real evidence from Google and Facebook and so on, while they are operating their systems, which have been thoroughly tested at manufacturing time, they're running into all kinds of problems. So this is a very clear evidence that currently testing methodologies are not sufficient, and we don't think that it will be. So kind of this resilience features and protection is important in the field.
Yeah, thank you very much. Can we also extend the same question for testing chips while they're working in the field?
Yes, so that's exactly the work that I showed you a little bit earlier. So we do have a technique that allows the chip to continuously be tested in the field while they're working, right? But the key question is that there is the cost, right? We need to consider the cost when the machine is running. How does it affect the application performance, power, and so on? And secondly, what we're going to test, right? And then there are also, of course, like other follow-up things from there, lots of interesting kind of architecture that we can do. Let's suppose that we find a problem, how do we localize it maybe to a particular space or location in the hardware? And so there's interesting architectural opportunities to also enable self-repair architectures after we have found failures and so on. So really very exciting opportunities in that space.
Yeah, thanks for the answer.
Yeah, great. Very good questions, and I'm really happy that I'm already seeing questions. Really like this interactive kind of discussion. So if anybody has any more, please get them my way. So let me just get back to sort of this deep dive, right? So we talked about that we want to understand how transient hardware failures can corrupt an entire training process for deep neural network. So this is sort of the outline of the presentation. So I'll first provide some background materials, and then I'll talk about our resilience analysis methodology, and then I'll provide the key results from our analysis. And finally, based on our findings, I'll be talking about new mitigation techniques. So let me start by quoting this keynote from Google, which tells us that hardware failure challenges are urgent and critical in deep learning training accelerator systems. They call these problems bugs from hell. So as you know very well, today, neural networks are very large and complex, and they can take a lot of compute resources and a lot of time to train. One example that's given by Google is this 4 trillion parameter transformer network. And to train this network, they need to use 2048 core TPU V4 systems, and it takes 10 days. And if you do your math, this is yottaflops. So what happens if a hardware failure or bit flips occur in one of the training devices at some point during the training process? And what happens if we don't even know that a hardware failure has occurred? This can cause all kinds of troubles, and this is exactly what Google has experienced. So they were running some deep neural network training workloads. Deep learning training consists of many iterations to minimize the loss value of a loss function. And in each training iteration, there's a forward pass and also a backward pass. The forward pass basically takes in a mini batch from the training data set and calculates the loss value. In the backward pass, the gradients of the weights and the inputs of every layer are then calculated through backward propagation, and then the gradients will inform how we can update the weights to minimize the loss value. So when Google was training these very large neural networks, at some point, they encountered what they called mysterious and difficult to identify problems. But it is not after many hours and engineering efforts later and that they spent on debugging their software system that they realized that there were no software issues and hardware is actually the problem. So even though the problems were eventually resolved, they have wasted a lot of time and a lot of resources. Moreover, among all of the failures that have been observed in the TPU systems, 75% of them are not reproducible. These not reproducible failures are the transient hardware failures that we talked about earlier, which are caused by various mechanisms such as dynamic variations, circuit marginalities, circuit degradation, and soft errors. And we also know that these hardware failures occur in logic because memories are largely protected by error-correcting codes. And prior to our work, there's no understanding of the impacts of these hardware failures on deep learning training systems, and not to mention any mitigation techniques. And this is where we came in. At that time, we actually already had an array of work to enable resilient deep learning accelerators, and we have already started to investigate how hardware failures can affect deep learning training. So Google got interested, and that's how we started the collaboration. Our work has made two important contributions. We have performed the first in-depth study to characterize and analyze transient hardware failures, targeting the logic portion of deep learning training accelerator systems. This is done by performing 2.9 million fault injection experiments. So we have a very comprehensive understanding on how hardware failures actually propagate and also interact with the training algorithm and process. And based on our findings, we have devised new efficient mitigation techniques. So as you can see here, the costs of our techniques are very small, and they only involve less than 32 lines of code change. So now I'm going to discuss our methodology for our resilience analysis. The base accelerator architecture used in our study is NVDLA, which is NVIDIA's open-sourced accelerator. The accelerator was originally designed for inference only, and it has a data flow architecture that has 4 different stages, as what I'm showing on the slide. The first is the input and weight fetching and pre-processing stage, which fetches the input and weight values from off-chip memory, performs some maybe data processing and padding, and then stores the values in one or more levels of on-chip memories. The second stage is input and weight sequencing, which dispatches each pair of the input and weight values to a compute unit. The sequencing logic is implemented based on a specific reuse algorithm, which allows an input or weight value to be reused multiple times to minimize memory access overheads. The third stage is MAC processing. MAC stands for multiply and accumulate, and there are usually a large number of these parallel MAC compute units to perform MAC operations, because MAC is the dominating operation in deep neural networks. And finally, in the last stage, it will perform Allen-normalized operations, it would apply the activation function, and then stores the partial or final results back to memory. And even though NVDLA was designed as an inference accelerator, it turns out that many different deep learning accelerators, they actually share this very common data flow architecture. And also, the microarchitecture for both training and inference purposes is exactly the same because, again, the core computation is very similar. So NVDLA can also be extended for training purposes. And how do we do this? The change is actually very minimal, which only involves augmenting the data path of the NVDLA accelerator to support numerical precisions, which is more commonly used in training. So in our study, we used bflow16 for MAC operations and FP32, 32-bit floating point precision for element-wise operations. In addition to that, the only other changes we need is the compilation flow in the backward pass. We need to reorder some of the tensors there so that the elements of the tensors can be passed into the accelerator in the correct order. But this change is just for the compilation phase. It can be done statically and no hardware changes are needed. For resilience analysis, the most widely used approach is statistical fault injection. So basically, we inject randomly chosen faults, and the faults are basically just abstractions or hardware failures. So we'll inject these faults into the execution of a system, and then we'll compare the outcome with the fault-free run. And of course, we do this for many, many samples to really understand statistically the effect of the different hardware failures. We can perform fault injection in hardware or software. Hardware fault injection techniques are accurate, but it is extremely slow. And also it requires access to RTL, which may not be available. We can also do fault injection in software, which is much, much faster. And also we don't need access to RTL. But the problem is that it is typically inaccurate. There's also some resilience studies on deep learning accelerators, but as we mentioned before, they're really limited in scope and they focus on memory errors only. So let me get into some details about why software fault injection is inaccurate. It is because in the software level, we cannot easily capture complex hardware behaviors. For example, in software fault injection, a transient hardware failure is typically modeled as a single cycle bit flip in a single architectural state. However, in hardware, the accurate representation is actually a single cycle bit flip in a flip-flop. But this can lead to many possibilities in the architectural level. For example, we can have a single bit flip, we can have multiple bit flips that affect one or more architectural states. And we can also encounter other system anomalies, such as timeout. So this is a more concrete example, which we're demonstrating using NVDLA. I'm just showing you a very small portion of the weight data path that carries the weight value to the MAC units in a forward pass. So as you can see, let's say this bit is being fetched. And let's say in this flip-flop, right, we have encountered some sort of a hardware transient hardware failure, and it flips the bit from 0 to 1. Now, this faulty value is going to propagate to MAC unit 1. And as you can see, because we have a feedback loop in this flip-flop, the effect is that this failure would affect 16 different output neurons consecutively in the output. So as you can see, the exact behavior actually depends on, of course, the implementation of the architecture, and it cannot be captured by just simplistic software fault models. The limitations of existing techniques motivated us to create this new resilience analysis framework. It's called Fidelity. It overcomes all limitations of previous work because it is fast, it is accurate, and it does not require access to RTL in most of the cases. So I'll tell you what I mean just in just a few slides. It is also capable of analyzing transient hardware failures in both logic and memory, and applicable to a wide variety of deep learning accelerators. The fault model for hardware failures in logic is single cycle, single bit flips in the flip-flops, which is the most widely accepted fault model that accurately captures the behavior of transient hardware failures. And in a deep learning accelerator, and for our fault modeling purposes, we classify the flip-flops into 3 different categories. First, we have the data path flip-flops, which store the weight values, activation values, partial sums, and any other intermediate values of various computations. We have data path and we also have control. So these control flip-flops are used to control how different data path values are streamed into different data path flip-flops. The control flip-flops can be further categorized as local or global. Local control flip-flops affect only one or a few data path flip-flops, while the global ones control a large number of the data path flip-flops. So a fault in a global control flip-flops can pretty much affect a large amount of computations in a deep learning workload. So one example is the flip-flops that are used to specify the numerical precision of the current computation. So as you can imagine, if a bit flip occurs in one of these global control flip-flops, let's say, we were supposed to perform bflow 16 operations, and now int 8 operations are being performed, then pretty much all computations, all outputs in the entire neural network layers will be affected. So to model the bit flips in the data path and control and local control flip-flops, which are actually the majority of the flip-flops in the NVDLA architecture, we use a systematic approach called reuse factor analysis, or RFA. So we'll spend some time to get into the details of this technique. But for global control flip-flops, we actually need to consider them differently. Global control flip-flops accounts for 10% of the total flip-flops in the design. And for inference, as I mentioned before, they would basically incur large perturbations in the computation. So the inference result would always be different in most of, or almost always different from the fault-free run. So we can just model the bit flips as, always a fail outcome for inference very easily. For training, however, this is different. This is not true anymore. Even though the bit flips in the global control flip-flops can cause big perturbations in the computation, the training process and algorithm may still be able to recover, right? So now we also need very accurate fault models for these global control flip-flops. So the only way that we can do this is actually to analyze the RTL systematically. And this is exactly what we have done. Then by analyzing the RTL, we have derived 12 different accurate fault models, which are already sufficient to cover the behavior of the bit flips in the global control flip-flops. So all the details are in our paper. But what I want to focus more on is basically for analyzing the bit flips in the data path and also the local control flip-flops, which account for the majority of the flip-flops in the design. So as I mentioned, the approach that we use is called reuse factor analysis, or RFA. So here is the key idea. We leverage the unique architectural and application properties of deep learning accelerators and also the workloads. So let me now tell you what these properties are. The first property is that one fault can only directly affect the outputs of the current layer. So in our framework, we first determine the effect of the fault in the current layer, which include the locations and also the values of the faulty output elements. And then in the second step, we perform accurate software fault injection at the layer's output according to the results in step 1. So the fault can basically, the effect of the fault can keep propagating in the software level. So really step 1 is the key. But how do we determine the effect of the fault in a current layer? We turn to the second property. One fault affects a deterministic set of output elements in a current layer due to the regular structure and well-defined data flow and reuse algorithm, which are common features in deep learning accelerator architectures. Now, leveraging this property, we created the reuse factor analysis for step 1. The input of the reuse factor analysis is minimum amount of hardware information, and the outputs are the accurate software fault models, which are used to perform software fault injection simulation in step 2. And here are some more details on the inputs for reuse factor analysis. Given a target flip-flop for which we want to model the fault behavior, we need to know if the flip-flop has a feedback loop and also its connectivity and relationship with the map units. And we also need to know the data flow and reuse algorithm in the accelerator, which tells us which output elements are computed by each of the MAC compute units. And notice that all of these inputs can actually be obtained from just high-level descriptions of the architecture without the need to actually access RTL. So here is our algorithm. In the high level, the algorithm first captures target flip-flop to MAC unit relationships. And we consider both the temporal factor and spatial factor. The temporal factor accounts for the case where one flip-flop value is reused by one MAC unit for multiple clock cycles. And the spatial factor accounts for the case where one flip-flop value is used by multiple MAC units in parallel. The algorithm also captures MAC to output relationships. Then it bridges the two relationships together to create a connection from a bit flip of the target flip-flop directly to the positions of the faulty output elements. So let's now apply our reuse factor analysis to the NVDL weight data path example that I showed you earlier. So you can see that we only need this very high level information shown here for the reuse factor analysis approach. And then by plugging in these input values to our algorithm, we can see that the exact correct set of faulty output neurons are being returned by our algorithm. Now, the next question is, how do we determine the faulty output values? So here's the third property that we're going to leverage. Yes, there's a question?
Yeah, can I ask a question before that? So the algorithm you just showed seems like, depending on the size of the neural network, this can require a lot of computation. Is that correct? Are there some shortcuts in here?
Yeah, so neural networks themselves, of course, can be very big, right? But the algorithm actually depends on the architecture of the accelerator only. So the accelerator is not possible to run like the entire neural network, like just flat, right? And just map to the architecture. They're basically definitely broken up into different chunks, right? That the accelerator can process. So our algorithm actually does not, we don't care basically how big the neural network is. We only care about the architecture. And now I think what your question is that when we're affecting the 16 faulty neurons, right, there can be lots of possibilities, like, because it's just 16 faulty output neurons, but this output neuron space is very large. So where is it exactly, right? That's actually basically also tied to the fault, the original fault that we have selected. And based on that, because we also know how the neural network is mapped to the architecture, we can tell just by the data flow and the reuse algorithm in the accelerator exactly which faulty neurons are being affected.
Yeah, makes perfect sense. Thank you.
Yeah. Okay, great. Good question, by the way. Okay, so we're here right before the question. So now I'm going to tell you how we can determine the faulty output values. So here, there's this third property that we can leverage. We know that the data path flip-flops match the software variables very closely because it's an accelerator design. So any data path flip-flop bit flip can be mapped to an equivalent set of bit flips in software. So we can just basically perform this mapping and obtain the faulty output values from software simulation. So here's our final challenge. How do we perform reuse factor analysis on all of the flip-flops, right? Because there are typically a very large number of flip-flops in a deep learning accelerator. So fortunately, in deep learning accelerators, bit flips and data path flip-flops in the same pipeline stage and also belonging to the same variable type have the same effects. So we only need to perform reuse factor analysis for a few categories. And also the outputs affected by a local control flip-flop are exactly the same as those affected by the corresponding data path flip-flop. So this is a tractable problem. We have thoroughly validated our framework against 40,000 RTL fault injection experiments. So basically, we introduced the same set of bit flips in both the fault injection experiments using our framework and also using RTL fault injection. Our results show that the set of outputs that are affected by the fault in the neural network layers, they match exactly between the RTL injection experiments and also our framework with similar distributions of faulty values. So this actually covers, all of the data path, local control, and global control flip-flops. So this means that with 99% confidence, less than one fault in 1 million faults are not correctly modeled. So our framework is highly accurate. So now we have this framework, we immediately put it to good use to perform large-scale fault injection experiments. We have included a diverse set of representative neural networks, which can perform various tasks such as image classification, object detection, and natural language processing. They have different neural network features, and they use different optimizers. These diverse features allow us to perform a comprehensive characterization and analysis of how hardware failures affect deep learning training. We have performed 2.9 million fault injection experiments to obtain highly statistical significant results. And of course, we can run such large number of fault injection experiments because our framework enables very fast speed and also accurate at the same time. So here are our results. We have characterized the training outcomes, and here we're showing the breakdown of the different outcomes. So as you can see, a lot of the injected faults, around 85 to 90% of them, depending on workload, do not actually affect the training outcome significantly. So these are the green bars on this figure. Some of the injected faults, around 10%, result in those numerical errors, such as infinity values or NaN values. But these are very easy cases. Pretty much we see these numerical errors and we know that some problem has occurred. But the most interesting cases are what we call the latent unexpected training outcomes. These outcomes have not been reported in any of the previous work, either in the literature or by industry. These latent outcomes are called slow degrade, sharp slow degrade, sharp degrade, and low test accuracy. Even though they only account for a small percentage in our experiments, this can still translate to frequent occurrences in large-scale data center systems today with millions of training devices. And the frequency of occurrence is expected to increase further as the systems scale in the future. All of these unexpected outcomes exhibit abnormal training convergence trends, and they can take a long time to identify because even when the effect of a hardware failure propagate and perturb the current training iteration, it will not be immediately clear how this perturbation will eventually affect the final training outcome, right? Because training is an iterative process and things can be recovered. So the overall convergence trend will take a long time to emerge, and we really can't observe the overall trend until many, many training iterations after a failure actually occurs. And only at that point, we will be able to conclude that something is fundamentally wrong with the training procedure. And one thing I want to highlight here is that after our experiments, my student went to Google for an internship, and during his time here, he observed some of the latent effects in real machines as well. So it's not just a simulation effect. But how does one single cycle bit flip in a single flip-flop introduce these latent effects, right? That basically corrupt the entire training process. Now I'm going to answer this question, and I will use the slow degrade latent outcome as an example. For these cases, after a fault is injected, the training accuracy slowly degrades, and then it stays at a low level for many, many, many training iterations. Theoretically, the training accuracy may recover slowly eventually, and then the test accuracy just follows the trend of the training accuracy. So after our deep analysis, what we found is that in the experiments that we had, the slow degrade cases only happen when the optimizer is Adam. So what's special about Adam? It uses a momentum value, which keeps track of the history of the gradient values from previous iterations and combines them with the gradients of the current iteration to update the weight values. And what happens is that because of an injected fault, the absolute values of some gradients in a current iteration becomes very, very large. Now, because the momentum keeps track of the history, even though the hardware failure itself is transient, the effect of the fault actually persists for many iterations afterwards because of this history value. So for many iterations, the history value dominates the momentum value. So the gradient of the current iteration actually has no effect on the way update. And so the accuracy degrades slowly. Because of a decay factor that is applied to the gradient history, the magnitude of the momentum will slowly decrease as well to a small value. And then if you do your math, basically this would tells us that the value would pretty much decay to close to 0. But notice that at this point, the gradient history values are actually still much, much larger than the gradient values computed at these iterations. So the gradient values are still having no effect on the way update. So the accuracy continue to stay at a low level. Also because the momentum is 0, so we're not really updating anything. And then in theory, because of this decay factor, the history value will eventually drop to a small enough value so that the gradients can affect the way update again. However, how long it takes to reach this phase 3, this recovery phase, actually depends on various factors such as the specific network, the training dynamics, the decay factor values, and so on. So in practice, we may never reach this recovery phase. And this is what we have observed in our experiments as well. In the majority of the slow degrade cases, we did not see this recovery effect, even after doubling the number of training iterations compared to the fault-free run. Similarly, we have done a very thorough failure propagation analysis on all of the latent unexpected training outcomes. We won't have time to go over all of them today, but the details are in our paper. From our analysis, we have obtained the necessary conditions that must be satisfied for a hardware failure to generate a latent unexpected outcome, which are the difficult cases that we must be able to handle. The necessary conditions are large absolute gradient history values in optimizers or large absolute moving variance values in normalization layers. What's more, these necessary conditions must occur within 2 training iterations from when a fault is injected. Leveraging these necessary conditions, we have devised new hardware mitigation techniques. This is a high-level mitigation flow. We need a failure detection mechanism. And then once a failure is detected, we decommission the faulty hardware for further diagnosis. And then we also need to relaunch the workload that is affected by the faulty hardware to a healthy device to recover the workload. As we mentioned previously, the existing detection and recovery solutions tend to be costly. Our idea is to leverage the necessary conditions that we have obtained from our large-scale experiments and analysis to detect hardware failures that are likely to cause the latent unexpected outcomes. For detection, all we need to do is to check large increases in the absolute gradient history or moving variance values, because these are the necessary conditions. For recovery, because we know that these necessary conditions must occur within 2 training iterations, we can simply re-execute the last 2 training iterations to recover the workload. Now, the only one key question that remains is that when we say we want to check the large increase in these values, how large is large? And it turns out that just based on the mathematical properties of neural networks, we can derive these bounds. And we have a detailed proof in the paper. So if you're interested, all the math is there. And using these bounds for detection, 100% of the latent unexpected outcomes in our fault injection experiments can be detected. We evaluated our detection and recovery techniques on the Google Cloud TPUs. The implementation involves only less than 32 lines of code change. In terms of performance, in the absence of hardware failures, the detection technique itself introduces very small performance overhead, less than 0.3% across all of the workloads. And we have compared our technique with a state-of-the-art algorithm-based fault tolerance technique. which is one of the state-of-the-art detection technique, and ours is 166 times better. In terms of recovery, the cost in terms of performance is also very small, less than 0.16%. So this translates to up to 500 times better compared to the common checkpointing technique, which is commonly deployed in deep learning training workloads. So in conclusion, hardware failures are big threats to neural networks, and even for training. Through tackling this significant challenge, our work has filled two important knowledge gaps and enabled potential technology transfer opportunities. We have performed the first study to characterize and analyze hardware failures, specifically transient hardware failures that occur in the larger portion of deep learning accelerator systems. So now we have a comprehensive understanding of their impacts on these workloads. We have open sourced our framework, and we're also planning to actually also open source the data sets from our fault injection experiments. And then based on the new knowledge, we leverage the necessary conditions to devise new, effective, and lightweight mitigation techniques. These techniques only require very minimum software changes and no hardware changes, and they incur very minimum overhead. So they're readily deployable in practice. We believe that our techniques can actually also be extended for other systems, such as GPUs and CPUs as well. So this is the everything that I have for my presentation. I think we have some time left, and I'm happy to take any questions.
Thank you very much for the presentation, Professor. I will start with a question from YouTube again. Kyan Song is asking, could you please comment on the accuracy of the failure detection method, e.g. false positives? Do you think the problem of ML training failure detection is solved after this?
I think the problem is solved, right? I think he mentioned false positives.
Yeah, so the question says, could you please comment on the accuracy of the failure detection methods?
The accuracy. So, yeah. So after we have detected, so basically when we have detected this failure, right, we also have a recovery action here. So let me just go back to this slide, right? So we have, we basically detect the problem and then we recover by re-executing the last two training iterations. So we know that these necessary conditions that we use for detection always occur within two training iterations of the from when the failure actually starts, right? So if we roll back two iterations, we can basically roll back the workload to a state where the failure has not affected the workload. So using this detection and recovery approach together, the accuracy of the training will not be affected. It's just as if it's going to do a for-free run. It will be the same. So whatever the original training algorithm will give you, this is what our technique would give you.
I think that's a fantastic answer. Thank you. Okay, there are more questions on YouTube.
Great.
Regarding your findings within the fault injection and analysis framework, it was missing the real mismatch distribution. Could you please comment on this?
The mismatch for which one?
The real mismatch distribution. Yeah.
The real mismatch.
There are no details here, so.
This is for the framework, the resilience analysis framework, or which mismatch is referring to? I guess I missed that part.
It's about fault injection and analysis framework. I think it's referring to the resilience analysis framework.
The resilience analysis framework, right? Fidelity.
Yes.
So yeah, let me also go back to there. I believe I mentioned, okay, let's just, instead of doing that, I'll just come back here instead of just going up. I think here, right, is this slide in particular that they're talking about? I'm not sure. I'll just mention this. Yeah, I think I'm missing one slide there. So basically, when we validate our framework, again, we're comparing basically the effect, right, the fault effect that our framework basically gives to the RTL fault injection for each layer. And we found that the outputs, right, the elements in the output tensor, they match exactly. And for the data path flip-flops, the values actually also match exactly. For global control and local control flip-flops, we can't really, it would take basically a lot of detail, like almost like detailed RTL simulation if we also want to match the faulty values exactly. But we are able to basically model them with a similar faulty value distribution. So overall, the faulty value distributions are also similar for those. So for data path flip-flops, everything matches exactly. For the control flip-flops, they're basically the locations that they affected match exactly, and the faulty values have a similar distribution between the RTL and our framework.
I think that answers the question. Thank you very much. I have another question. It's a bit maybe out of the topic, but the talk was focusing a lot on bit flips occurring in flip-flops. And it's really important. I agree with that, because when you have a bit flip over there, it can affect like many things. But did you also extend this work for covering the bit flips that might occur in SRAMs, DRAMs, some other memory structures, other than, yeah?
Yeah, so our framework, the fidelity framework, is able to also model those effects. For memories, it's a little actually easier than logic, because even if it's a bit flip in memory, right? Once the bit is flipped, then that value will stay in memory until the next time it's overwritten. So the effect is more persistent.
Yes.
So we believe that our framework, the fidelity framework, can also be applied to those bit flips as well, using exactly the same methodology, the reuse factor analysis and so on. We can model those exactly. So it can be done. We didn't do those studies ourselves, because for inference, I think there's already a lot of work out there. So for example, like I think even like NVIDIA, they had a bunch of even like real like experiments showing, if they inject some bit flips using actual like neutron beams or whatever, how would that affect different things? And then for training, a lot of these devices, as I mentioned, like their memories are already protected by error correcting codes. So we feel that there's already, for training, there's not much of a need to conduct those analyses, because that is not the main problem. And for inference, there's enough work out there that is looking at that. So really the main contribution from our work is that we also cover the logic, even though our framework can also be used for memories.
Yeah. Thank you very much. Yeah, that makes perfect sense. I'm not sure if there are more questions in the audience. I'd like to invite everyone to speak up. But meanwhile, I will ask another question if you have time.
Yeah, sure, of course.
So, so if I'm a software engineer or an AI expert, let's say, I'm designing a new neural network. So based on your experience, would you have some like some recommendations, suggestions to for me to make my network more resilient to this kind of errors, such as like does it make sense to go for weightless neural networks, or should I like what kind of quantization, for example, I should choose? If I use like many bits for one weight, now maybe a bit flip might affect the value less, but now I have a more footprint, let's say, and then I'm not sure like what. So I cannot picture the trade-off in my head if it makes sense to go with like one direction, like use more bits or less bits. You know what I mean? So
yeah,
do you have any recommendations towards this way?
Yeah, so that is another way of thinking about resilience. We can devise deep learning techniques, right, that may be more resilient to hardware failures. We did have some observations, but it actually depends on whether you are talking about inference or training, right? For training, I would say typically you don't want to worry about hardware failures, because maybe you are experimenting with a new network or doing like new things, very new things, right? That we don't even know, like, because I'm not a machine learning expert, right? They can be doing all kinds of like new topology, new architectures and whatnot. So I think we should allow the machine learning experts to have their freedom to explore whatever they want and not restrict what they're doing, right? So I think it's better not to like kind of have that kind of mindset. At least that's what my philosophy is. But if people want to do things that are more basically resilient, there are definitely approaches. So as I mentioned, like one of the necessary conditions is that the error must first have caused like this very large like gradients, right? So if you use some sort of gradient clipping technique, that would help if that's already in a training process. It does not help with everything, but it can help make the network a little bit more resilient. And then also in our paper, we also discussed the effect of normalization layers. If you get rid of them, they would have different effects. Normalization layers such as batch norm, however, they're pretty commonly used. But if there's an approach that allows you to, train your network still in a very stable way and achieve high accuracy without those normalization layers, we could see some different effects. So for inference, there are definitely some other techniques. So there's a lot of work out there talking about also like large disturbances in some of the intermediate output activation values. And if we can somehow clip them, then that would help with also constraining the impact of any errors that occur. And then normalization layer, I guess, is also another common factor. If there's any error that occur because of a normalization layer, usually those error effect would also be tapered by those layers. So if you can actually include normalizations in inference, you would also see sort of, I guess, a better tolerance to failures that could occur. So there are different ways, but I feel like, for solving these problems, it may be better to solve this from a system level, and we allow the application ML designer to do whatever they want.
Yeah, definitely. We have more questions on YouTube chat.
Yeah.
I have one.
Rahul, go ahead, Rahul.
Question. Yeah, can I go ahead?
Yes, please.
Yes, please go ahead.
Yeah, so I have thanks for the great talk. It was very informative, right? So I have like one simple question that might sound very odd. So the detection technique that we are discussing here is like 100% accurate in a sense that whenever it says that there is a hardware fault, it is indeed a hardware fault, right? And then we have so you showed somewhere in the like how large is that threshold that we are looking for, right? And then there are exactly mathematical proof behind this thing that says that 100% of the latent unexpected outcome cases are detected. So is there any false positive cases also, like you detected that it would be a hardware error, but it's actually not a hardware error, and then we identified something as a potentially false positive hardware errors?
Yeah, I can answer that, and I don't think it's kind of like a simple question or what. It's actually a very good observation here. So what I mean is that I use this bound, right? But remember, this is a necessary condition, not a sufficient condition. So even though sometimes we can see this large increase in these bounds, right? We detect, things are out of bound. Maybe they don't lead to latent unexpected outcomes. So by using our method, we'll detect cases that both lead to latent unexpected outcomes and also those that do not lead to latent unexpected outcomes. But in either case, this means that some failure has occurred in the system because the bounds are derived mathematically, which means that, following, the certain properties, the value should not exceed this bound. So we know that for sure there's a hardware failure that has occurred. Whether the hardware failure actually lead to unexpected outcomes, it would depend on a lot of different factors. And our detection techniques does not distinguish these two cases.
So that also means that this detection technique is not necessarily tied to the optimizers that we are essentially using, right? So every optimizer would have their own way of, incorporating the momentum inside, so that if we see sudden like a drastic change of momentum from iteration to iteration, then we can definitely say it's coming from a hardware error. But whether it would materialize eventually, that we don't know.
Yes, exactly, right? And these bounds are derived, if you use a different optimizer, we need to use a different set of math, right? So what we have in the paper is for Adam and some of these others, but you can follow the same thing. Like it's basically just math. We can
Yeah,
always,
yeah.
yeah, exactly. Very good observation. Yes.
Thanks.
Yeah, I have a follow-up question on that, just to clarify one thing. So there are also other errors that don't cause latent unexpected outcome that we're potentially not interested in because they don't result in catastrophic failure, right? And those are also sort of out of the scope of this detection mechanism, I think.
It's not exactly, I would say it's not exactly out of scope. I think our detection method pretty much takes care of all the difficult cases. And then there are simple cases. The only thing left is basically the NaN and infinity values that can occur during the training process. But those are obvious, right? Because they, first, our observation is that they actually occur, pretty immediately after the failure has occurred, usually within one or two training iterations. And you see like you have an inf, right? You have a NaN. So it's already detected because it's a visible symptom. And then by using our recovery technique, it actually also recovers the workload. So I would say this whole, the only thing that we need to add is basically this bounce checking, and then we cover all cases.
Okay, yeah, that makes sense. Thank you.
Is there any mathematical, let's say, expectation to pinpoint the errors in the flip-flops? Like, is it possible?
Yes, that's a very good question. That's actually a work that we're working on right now. And I'm happy to talk to you offline, actually, if you're interested.
Okay.
We do have techniques for that. So yeah, send me an email and I can talk more.
That's perfect. Okay, thanks.
Yeah, it's very important, right? We know that there's an error, but if we know exactly like where the error occurred and how it occurred, it gives us a lot of information to basically enable, what I call the self-repair architecture. And also we can collect, all sorts of information that would maybe guide us to build better systems in the future. So it is a very important research question. And yeah, what we're working on right now.
So we have one more question on YouTube. I'll just read it.
Yeah.
Do you have plans to tackle hardware failures in general computations, not limited to machine learning? And what do you think would be promising ways to approach this problem in a general setting, like hardware OS, application level detection, replication in field testing, and trade-off between generality and performance overhead?
Yes, so there's a lot of work in that space, including some of the work that I have done in my group. So it's really its own topic in its own. So I would just say that this perspective about involving a cross-layer perspective into solving a whole problem is very, very important and very interesting one. I think one of the paper maybe you may find interested in is this paper called Clear. So it's published in, not by me, but from one of my previous group at Stanford in DEC 2015. So again, feel free to send me an email if you want to read in that work. But basically, we analyze different approaches from different system design layers, and we have a methodology to determine basically what's the best combination of different approaches to use. So there's definitely a lot of different techniques that can be implemented in the different layers of the system design stack. And it's a very interesting question to think about how to combine them in a most optimal way. And definitely that's an interest of mine as well. So definitely happy to have more discussion on that as well.
Yeah, thank you very much for the answer. I think I already found the paper. I will just put it on the YouTube chat.
Okay, great.
And I had a question earlier on, actually, I wanted to ask, but it's kind of out of topic also. I'm wondering if you have any insights into if the manufacturers of these devices that do the computation have considered the fact that there could be a lot of errors. But the applications they were going to run are going to be resilient anyways. So did they go like, oh, let's not implement any hardware, redundancy techniques because the applications will be tolerating them anyways? Or are there already redundancy techniques in the hardware and we're observing these errors despite them?
Yeah, so typically in today's systems, there's not like expensive redundancy techniques, especially when you're talking about data center servers, because those servers, they're cost sensitive, they're not like those high-end enterprise safety critical applications, right? Those systems, they would have some sort of redundancy. But in data center systems, no. Currently, there's no technique, right? So that's why, we're seeing all these silent data corruption challenges that are happening in real servers in data centers by, as you see being reported by Google and Facebook. So the question is, we could do redundancy, but that's very high cost. So obviously we need better techniques, right? In different ways, both from manufacturing testing to sort of this in the field, different techniques from different layers to really handle this kind of failure effect. And the application kind of property that you mentioned is an interesting one. So there are techniques even in the algorithm and application level that could make the algorithms sort of also more tolerant to failures. So I think we already touched this, right? But there's many opportunities to think about different ways and protect things in the most optimal way. There's more than one way of doing things. For machine learning, I think, as you can see from my talk, I don't think that we can only just rely on the application property because there's no guarantee that they can tolerate everything. They can tolerate something, right? But it's really the thing that they cannot tolerate that we need to fix.
Yeah. Yeah, that makes a lot of sense again. Thanks.
It was a very insightful and educational talk. Thank you very much. I don't see any other questions unless there are there any burning questions in the audience? I guess we have around like 20 people on the call. I guess not anymore. Yeah, thank you very much for the talk, and I hope to discuss these more in the future as well.
Yeah, I'm happy to be here, happy to have this interaction, and feel free to reach out to me if you want to discuss more. Welcome.
Yeah, thank you very much.
Okay, thanks everyone.
Bye.